Hello, Algebra 2 students. This is the third review getting ready for the semester exam. And actually, if you remember back that far, we actually broke Unit 2 into two pieces. It was very long, a lot of information in it, and actually it kind of bridged right over the end of the first 6 weeks and the beginning of the second 6 weeks. And we needed a second test for the first 6 weeks, so we kind of broke Unit 2 into a first half and second half, and this is the second half of Unit 2. So this is what we called Unit 2B, and one of the very first things we got into was inverses. Now, inverses is one of the things that you've heard me fuss at you many times throughout the year because it is a very simple concept, and some of us just never did bother to learn the rule. Okay, an inverse of a function is found by reversing the variables in an ordered pair and resolving the equation for y. Now we saw a shorthand notation for inverses. It is the function typically denoted as f to the -1 power. It kind of looks like an exponent, but it's not read f to the -1. It's read the inverse of f. Okay, and it's really a very simple concept. Anytime you need to find the inverse of an equation and you already have the equation, simply take x and turn it into y, and take y and turn it into x. Now, probably you had y isolated before you did this. Now it is not isolated anymore because it just changed places with x. So all you need to do now is follow your basic Algebra 1 steps for solving an equation and resolve the equation for y. Get y back by itself. Once you've done that, you have found the inverse. Okay, so we worked through some examples, and you're more than welcome to look back at that lesson if you are struggling with that. Okay, but very simple concept. No reason for us to still be missing that. Now, what we saw is there are sometimes some things that can show up in equations that are a little bit more difficult to deal with when you are trying to re-isolate your y value. And some of the things that we ran into that can be more complicated are logarithms, absolute value bars, and exponential notations. Okay, so while we're resolving the equations for those things, it becomes necessary to know how to counteract those things inside of a problem. So the first thing we looked at was the absolute value bars, and the idea of how do you get the bars off of a particular expression. Like in this particular case, we're looking at the inverse of h of x, and we can see that y is inside of the absolute value bars now because of the inverse. Well, to get to the y, we have to get the absolute value bars off of the y. Okay, so how do you get the absolute value bars off? Well, we run into a little bit of a sticky spot in our algebra because of this. And the problem is that y minus 2 is an unknown value. Okay, and we know that absolute value bars are going to steal the sign of any value that is inside of them. Well, if they're going to steal the sign, well, we have a problem. We might have a y minus 2 that is some negative number, and we might also have y minus 2 that is some positive number, and we have no way of knowing which one it is. So in order to be entirely accurate, we must consider both possibilities, that y minus 2 is positive and y minus 2 is negative. So when it comes time for you to take the absolute value bars off of an unknown number like we are doing now, you must basically break the problem into two problems. One treating the unknown value, in this case y minus 2, as if it is a positive number like we're doing on the left there, and in a second case where y minus 2 might be a negative number like we're doing on the right side. You proceed to solve the problem from there, continue isolating y, and you will end up with two different values for this y value for the inverse. Okay, and they are both correct. Basically what it means is the graph is going to obey one type of an equation up to a certain point, and then after that point it's going to obey a different type of equation, and that's where you get that direction change in an absolute value graph. Okay, another thing that we ran into is the idea of logarithms and exponential equations. Now, we'd already looked at these as far as their parent function status, okay, but one thing that we did not know until now is that the logarithmic equation and the exponential equation are actually inverses of each other. That being the case, if ever you run into one of them in a problem and you want to counteract it or eliminate it in the problem, you can use the other side of it to counteract it. So if you have a logarithm that you do not want, you can always raise it to an exponent. And if you have an exponent that you do not like, you can use the logarithm to eliminate it. Okay, so it's just a little bit of getting used to, like the next to last step in this problem. As you can see there, you have 10 to the negative x, or I'm sorry, yeah, 10 to the negative x power, and we need to get that exponent down. And the one thing that we can do is we can take the logarithm of both sides, and that can bring that down. Or in this particular case, since the bases matched, we were able to cancel out the matching 10 bases. Okay, but anyway, sorry, I said that totally wrong. In this particular problem, in the last step there, we're trying to get to the y, and the y is the logarithm of the logarithm, and y is the argument. To get that argument away from the logarithm, we can counteract the existence of that logarithm by raising it to base 10. And of course, whatever you do to one side, you have to do to the other. The base 10 and the log in the exponent cancel each other out, and then y is the only thing left. Okay. In this particular case, when you go to work on your inverse, again, we end up with y in our exponent. Okay, we can't solve it as long as y is in the exponent, but we can counteract the base 10 by applying a logarithm to both sides. Log and base 10 are natural enemies of each other, so they cancel each other out. That allows that exponent with the y in it to drop down, and then we can work the problem. Okay. There were some more examples in there. Come in and ask questions if you're having trouble with that. Next thing we did was we started to explore the idea of logarithm, or the inverses of some of our equations in graphs. Okay, and what we basically saw here, and we looked at them one at a time, is in each case here in the center of the screen, you're looking at the parent function, and then on the right side, you're looking at the inverse of that parent function. And we looked at them all one at a time, and then we kind of all put them all on one screen together and said, okie dokie, what do you notice each and every time when you're looking at the parent function on the left columns and the inverse of the parent function on the right columns? And what we kind of discovered is that in each and every case, the graph itself is a reflection of itself through the parent linear function y equals x. And if that's the case, well, then that is the case. Basically, what we have discovered is that when it comes to the functions themselves, basically y equals x and x equals y. That is how come we are able to reverse the variables between the function and the inverse function without doing anything against the rules to that function, because y does equal x and x does equal y. Okay, now to make this a little bit more mathematical or scientific of a prediction, what we did is we looked at the ordered pairs themselves. Now, an ordered pair is broken down into two components. It's got an x component and a y component, which basically relate our point into the domain and the range. Now, specifically, the exact terminology for those guys is this value in the domain is referred to as an abscissa, and the value in the range is referred to as an ordinate. Okay, so an ordered pair is broken down into the abscissa, comma, and the ordinate. And as we've already discovered, okay, from a function to its inverse, the abscissa and the ordinate are going to reverse position. So if you have a particular location in two-dimensional space, in this case -2, 5, and you want to know where this point exists in the inverse, okay, you reverse the abscissa and the ordinate, gives you 5, -2, and that is the precise location of the inverse. Okay, and you can do this any direction that you want, as many times as you want. The concept remains the same. Okay, so basically what we did is we kind of figured out, all right, here is how we are going to graph unknown inverse functions. Okay, if we have a function, in this case y equals 1/100th of x cubed, we can pick test points all the way across the domain, and we can plug them into our equation, which is something we have done, about 500 times this year. And when we plug our x values into the equation one at a time, it gives us y values to go with it. So we end up with ordered pairs. Our ordered pairs turn into points, and our points turn into graphs. Okay, now to figure out the inverse of this particular function that you have going on, well, an inverse, all it does is reverses the abscissa and the ordinates. So the columns, the t-chart that you have on the left, your x's are going to become your y's in the inverse, and your y's are going to become your x's in your inverse. Okay, so all you have to do is reverse your columns, plot your points, and you have your inverse. Okay, that was that. The last topic that Unit 2 had to offer was the first time that we ran into asymptotes. Okay, and we basically learned that there are three particular types of asymptotes. There are horizontal, vertical, and oblique. And sometimes oblique asymptotes are called slant asymptotes. So the word oblique and the word slant are synonyms. Do not get confused and think they are two different things. It is the same thing, just a different piece of vocabulary. And what we did is we looked at a particular graph. We invented some points, we got some y values, we got some coordinates. Okay, and then what we did is we looked a little bit closer. You can see this graph is starting to turn as it approaches the y-axis from right to left. So I picked a few more test points in between +1 on the x-axis and 0 on the x-axis. Picked 1/4 and 1/2 and 3/4. Got 3 more points and plotted them, and that turned out to be a very good idea because the graph was turning fairly radically, and we would not have gotten the full effect of what this graph was doing had we not plotted those extra points. But based upon what we are looking at now, we can see that horizontally, as the graph travels off to the right, these points are becoming very, very flat. That means there is a horizontal asymptote. The graph is approaching some imaginary boundary that it will not cross over. And same thing on the vertical end of things. As we come to the left side of the graph is going very, very vertical. Okay, there is a vertical boundary that the graph is getting closer and closer to, but will not cross. And oblique would mean that there is a diagonal location somewhere in the graph that's doing the same thing, and there is no indication of that. Okay, so let's look at another one here real quick. Oops. Okay, again, got a nice neat diagonal line. It looks like there's going to be an oblique asymptote, but we can see the graph is looking like it's starting to turn toward the left end of our points. So good idea to pick a few more points in between 0 and 1 there to see what the graph is doing. And absolutely, very radical turn in the graph that you would have missed had you not looked at those smaller step sizes near the y-axis. At any rate, there does not appear to be any horizontal asymptote. There's not any points that are lining up going horizontally. But I think we can see, again, with the vertical right near the y-axis, the graphs are points are turning very vertical. And it's pretty clear to see the oblique asymptote in this graph. So we've got a diagonal boundary that's running through there that the graph will not cross. Okay, and we work through some more examples. Okay, that was that. And the last thing that we did was, instead of going through all of the trouble to try to identify the existence of an asymptote by getting all the points and graphing it and all that kind of stuff, we learned that there are things that we can look for in the equations that will give away whether a graph is going to have a particular type of asymptote or not. Now, in order to have a horizontal asymptote, your function's going to have to be rational, meaning there's going to have to be something going on in the denominator. Something is going to have the possibility possibility of zeroing out the denominator, and you can't do that if you don't have a denominator. So you're going to have some type of a polynomial, could be a monomial or binomial or trinomial going on in the numerator, and same thing for the denominator. It could be any type of a polynomial. It could be just a number, could be a variable, could be several variables. It just depends. Okay. Now, what we're doing is we're comparing the leading terms, the lead terms, and those are the guys that have the highest exponents to offer in both the numerator and the denominator. Okay, if the highest exponents are equal to each other, meaning possibly you have x to the third in the numerator and x to the third in the denominator, there is going to be a horizontal asymptote. Okay, if the numerator's highest power is smaller than the denominator's highest power, once again, you will have an asymptote. However, if the numerator's power ends up being larger than the denominator's power, then there will not be a horizontal asymptote. So those are facts you're just going to have to get memorized. If the powers are equal, then there is a horizontal. If the denominator's power wins, then there is a horizontal. But if the numerator's power wins, then there is not a horizontal. Okay. Once again, for the vertical asymptote, you must have a rational function. Okay. And the only time a vertical asymptote can happen is if there is the possibility possibility that the denominator can actually equal 0. Okay, so I think I said that backwards a moment ago on the horizontal asymptote. Horizontal asymptote is looking for the powers. Okay, the possibility the powers may equal, or the possibility that the denominator's power is larger. The vertical asymptote is simply, can the polynomial that's in the denominator ever equal to 0? That means you set it equal to 0 and try to solve it. See if it's possible to actually equal 0 or not. The oblique asymptote is a little bit harder to calculate, so we won't ever in Algebra 2 be actually identifying the equation of the oblique asymptote. Okay, but simply what we're looking for here is, once again, it's got to be a rational function, and this one can only happen if the highest power of the numerator is exactly 1 unit larger than the highest power of the denominator. Okay, so that's how come you're never ever going to see an oblique asymptote and a horizontal asymptote in the same graph together. It's because their definitions disagree with each other. Okay, the denominator for the horizontal has to be equal or larger for the horizontal asymptote, but for the slant asymptote, it has to be larger, but not just larger. It's got to be larger by only 1 value. Okay, so looking at our graphs here, like in this particular case, okay, we can look right at the equation and we can go, is there a horizontal asymptote? And the answer is yes, there is, because the highest power of the denominator is a 1, but the highest power of the numerator is a 0. There is no variable, so that's x to the 0. So you do have a larger power in the denominator than in the numerator, so it will have a horizontal asymptote. Okay, will it have a vertical asymptote? Is it possible that the denominator will ever actually equal 0? Well, yes, it is. What happens if x is 0? Then the entire equation says 1 over 0, so it does have a vertical asymptote. Now, since it does have a horizontal asymptote, there is no chance that it will have an oblique asymptote at the same time, but you can check it anyway. Oblique wants the highest exponent of the numerator to be 1 step larger than the highest exponent of the denominator, and that is not true, so no oblique asymptote. Okay, same thing, horizontal asymptote. Horizontal asymptote wants the powers to be equal, or for the denominator's power to be larger, and that is not the case, so no horizontal asymptote. Vertical asymptote, is it possible for the denominator to actually equal 0? Yeah, it is. Once again, what happens if x is 0? Then that would cause the entire fraction to be over 0, and that would cause a vertical asymptote. Now, an oblique asymptote wants the highest exponent of the numerator to be 1 digit larger than the highest exponent of the denominator. Okay, well, we got a 2 as our highest exponent in the numerator, a 1 as our highest exponent in the denominator. That fits the description, so yes, you do. Okay, you can look at more examples, and there are several in that lesson. Okay, and that is all of the information that showed up in Unit 2B. And of course, what we saw became a recurring theme throughout the entire year. The parent function stuff that went on in Unit 2A, if you never bothered to learn anything about the parent functions or their behaviors or what we expect from them, then you ended up getting pounded all year long as we continued to work on basically nothing but the parent functions and keep on expanding that knowledge. So those of you that kind of ignored me way back in the first 6 weeks where I told you if you didn't bother to learn this, it was just going to continue to haunt you all year round, you started to feel the pain a little bit on this. And then we ran into things like inverses in this unit, and I told you you better learn this because it's going to stick around all year long, and it has. But anyway, there is your Unit 2B review, and that is all.